Hey everyone, this is Mr. McLain teaching chemistry. This is a weird situation right now. We're all stuck inside trying to stay safe and stay healthy. Um, Even though we are in a weird situation, everything's up in the air right now, I do want to say that I'm going to keep teaching chemistry the best way I can and to the best of my ability. I'm going to be doing a lot of videos from now on. I think that's the best way to teach these topics of stoichiometry and the gas laws and thermodynamics and stuff like that. Those are really our next topics. I do not know how long we're going to be in this situation of quarantine. Um, I hope that it just kind of all goes away in a couple weeks and we're all back together. But if not, this is how things are going to be for the foreseeable future. And like I said, I'm going to do the best I can. Today, the topic is solution stoichiometry. And to be able to do this really well, to understand how you mix solutions together, here's my water bottle. There's stuff inside this water bottle, dissolved ions, salt, fluoride, probably a little bit of other stuff like sugars and things like that. Understand a solution, you have to understand the terms here. And these terms are hopefully review. So this is just a picture right here of salt water, good old-fashioned sodium chloride dissolved in water. And some new terms here. So solvent, a solvent is the stuff in which, the liquid stuff in which a solute is dissolved. And the solute is, in this case, the salt. The salt goes into water and then we stir it and it dissolves. Okay, so the solvent is, I'll switch to the blue pen because I'm using blue there. It is the substance in which the solute is dissolved. Okay, so in this case, for our purposes, water. Water a lot of times is a solvent. Most of our bodies is water, like 70% of our cells is water. That's because the solvent of our cells is water. All of our organelles, the chromosomes, all that stuff is dissolved in water. It's floating around in water. And the solute of salt water, or the solute of a cell, are all those organelles, all that stuff that is in the water. The solute is the substance that is added to the solvent, okay, and dissolves. Oops, dissolves. I'm going to try to use markers because it's a little bit cleaner and looks better, I think, on the screen. Now, when you mix these two things together, when you have all of that, when you have the solvent and the solute's dissolved in solution, you have what is known as a solution. A solution is a mixture of the solute and the solvent. So it's the total mixture of the solute dissolved in the solvent. So like salt water, you stir salt into water, it dissolves. You no longer see the salt in the water. And why does it dissolve? Well, you might remember that when the salt goes into water, like in the picture here, the ionic bond, NaCl, that bond is broken. Okay, the bond is broken, and the ions that make up the molecule sodium chloride, they break apart from each other because the water molecules pull the sodium and the chlorine atoms away from each other, and so you get Na plus over there sitting on its own, and Cl minus over there in the water sitting on its own as well. And if we were to draw a picture of what that looks like at the atomic level, let's use blue for water here. So water looks like this. Let's move that over a little bit. So this is something for the future. The water molecules, you may remember the water is a polar compound, and we have a negative side and a positive side to that bent structure. Remember that the water molecule has sort of a negative charge to the oxygen side, and the way that water is going to pull that ionic bond apart is water, because it's got that negative charge to the oxygen, is going to pull on the sodium side of sodium chloride. Sodium has that plus charge, and so they're attracted to one another. And so the sodium is going to get pulled away from the chloride. In the same way, the chloride, because it's negatively charged, it's going to be pulled by the water Don't know if you can hear that outside. It's kind of funny. People are being goofy. But remember that water has a positive side to itself as well. So that's the hydrogen side. It's a polar compound, so it's positively charged over on the hydrogen side of the molecule. And since chlorine is negatively charged, positive charges on the hydrogens and the negative charges on the chlorines, they're attracted to one another. And so in the same way, the water will pull the chlorine away from the sodium, and so you'll have ionization. I'll write that down as well. So why is something dissolving? Because water has the ability to pull these ions apart in the ionic bond and therefore ionize it. Ionization. Let's write that down there. Ionization. All right. So that's what's happening when we make a solution, particularly of an ionic compound. This isn't exactly what happens with like sugar, but something very, very similar happens, because sugar is not ionic. Sugar is covalently bonded, but at the same time, sugar is a polar compound, but it's a little bit more complex in that case. But for the most part, we're going to be dealing with ionic compounds being dissolved in solution. So one of the things we want to be able to figure out with this is, well, how concentrated is my solution? I'm sure if you just take a few grains of salt and put it in water, it might taste a little salty, but it's not particularly, bad. But if you go to the beach or something like that, that stuff's going to be really, really salty. So there's differing levels of how concentrated a solution can be, and that definitely affects the chemistry. If we're drinking water, there's a certain amount of salt in our water that's used to make sure that there's no bacterial growth, because salt inhibits bacterial growth. So when water filtration companies want to get water out to the people, they want to make sure that it meets a certain standard and doesn't go above that and doesn't go below that. There's a certain level of saltiness to water that you don't want to get around, or you don't want to be too far off. So we want to understand the chemistry of how concentrated solutions can be. And that, of course, that affects how, mixing things together, what do you make, and how much of that stuff can you make. Let me switch over to another piece of paper here. So the big deal topic with solution stoichiometry is this. The concentration of a solution depends upon what is known as its molarity. And there are many different ways to quantify concentration, but in a chemistry class, the most common way of doing that is with this topic right here, molarity. Molarity is a way we measure how concentrated a solution is, and it is equal to the number of moles of the solute, in this case, like our example, salt, NaCl, divided by the volume of that solvent in liters. And I'm going to change that a little bit. I'm going to change that to not solvent, I'm going to change it to the volume of the solution. Because if you add a lot of salt to water, that actually can change the volume of the solution. And so it doesn't matter how much water you add. It actually matters, well, how much space is that solution taking up. So not just solvent, actually the solution. So the volume of the solution in liters. Now, usually in a problem, you add like 5 grams of salt, and that's not going to affect the volume of the water you add very much. So for the most part, that doesn't matter. I just want to make sure that we're very clear. It's the volume of the solution. So if, for example, in the future, if you ever do science stuff, from my perspective, was in a lab once, and we had to make this like 13 molar solution of EDTA, and it required you to add like 250 grams. I can't remember how much it was exactly, but a huge buttload of EDTA had to be added to water. And so, it was a big big chunk of stuff, and that actually affects the volume of the solution, not just how much water I added. So I did have to take into account the solution's volume, not the amount of water I added. Now the unit for molarity is molar, or moles per liter. Okay, so these are, you say molar, if you want to say it's a 1 molar solution, that's the same thing as saying 1 mole of the solute divided by 1 liter of the solution. And then the abbreviated unit is a capital M. Capital M. One other thing to keep in mind is if, for example, I am talking about the concentration, the molar concentration of a solution like sodium chloride. Now I am going to indicate to someone that the solution has a concentration of 1 molar, for example. What I do is I write these square brackets around the formula of the compound. NaCl's molar concentration, that's what this means, writing it out like this, equals 1 molar, which would mean that there is 1 mole of NaCl in 1 liter of the solution. Okay? This would be a point where I say, does anyone have any questions? But since the entire room is empty, I'm not going to do that. I feel like I have to. So let's go ahead and put this. Let's go ahead and do some problems with this, just so we understand how to do it. And we'll do these together. So the first question here is, what is the molarity of a solution of 200 grams of barium hydroxide added to 0.50 liters of water? Okay, so what we're going to do here is we're going to figure out the molarity, and we have to remember our equation. Remember, molarity is equal to the number of moles of solute divided by the volume of the solution. I'll put SOLN for solution in liters. Okay. Now the volume they're telling us is 0.5 liters, so that's not a big deal, but they have not told us how many moles of the solute there are. So we're going to take this 200 grams of barium hydroxide and convert it to moles, and then we're going to divide. That's about it. It's really not that bad. So 200 grams of barium hydroxide, okay, and then we're going to go ahead and we're going to divide by the molar mass of barium hydroxide, and that would be, oh, I don't even have a periodic table thing. I should get a bad grade. So barium's down there. Barium has a mass of 137.3. So for everyone's benefit, 137.3 for barium. And then we've got 2 oxygens. So that would be plus 32, because 2 oxygens, 16 molar mass for oxygen, so times 2, 32. And then 2 hydrogens, molar mass of hydrogen is 1, so we'll just add 2 to that. So the molar mass of barium hydroxide here, 137.3 plus 32 for the oxygens, and then plus 2 for those hydrogens is 171.3 grams per mole. Okay, so I'm going to go ahead and divide 200 by 171.3. Okay, let's do that math. 200 divided by 171.3. So I get 1.17 molar, or 1.17 moles, I should say it that way. 1.17 moles of barium hydroxide. Okay, so 200 grams divided by the molar mass gives me 1.17 moles of barium hydroxide. And so the molar concentration of barium hydroxide, I'm going to write it like this. That is an A, is equal to 1.17 moles divided by, and the volume of our solution is going to be 0.5 liters. So 1.17 divided by 0.5, and that's going to give me 2.34. So the molar concentration is 2.34. And I would say 2.34 molar. You can say 2.34 moles per liter, but people are going to say on average 2.34 molar. Okay, so that would be the answer to this question. Let's go ahead and do one more kind of question. And then that's about it for today's lesson, actually. It's not much to it. It's just getting used to that molarity equation. And then I'll show you in just a second the homework. I'm not quite sure what to call it, but it's work to be done at home. And you do some questions regarding this stuff. So one more question here. What mass of CH3CH2Cl was dissolved in 300 milliliters of water to make a 2.15 molar solution? This is a really common kind of problem in a chemistry lab. You're told, hey, go make a 1.5 molar solution of blah, blah, blah. And you're told that. And you're not told anything else. And then you might ask, well, how much do you want? And then the person says, make 2 liters or 300 milliliters or whatever. And so you got to figure out on your own, how much stuff do I have to measure out of a bottle and then put it into the water and then stir it, and then I have my solution. So that's this kind of question here. How much stuff, CH3CH2Cl, ethyl chloride, that's what it's called, are you going to need out of the bottle to put in 300 milliliters of water to make 2.15 molar solution? Okay. So the way we're going to solve this problem is, again, we're going to use that molarity equation. So moles over liters. Just going to simplify it now. We want to have a 2.15 molar solution. That's what we want. But we want to know what mass of this stuff do we need. So we're going to have to figure out how many moles of this stuff, do I need to make this solution that's 300 milliliters in volume. And then from there, go from moles to grams. And then we'll be done with our problem. So what I'm going to do is I'm going to do 2.15 molar equals, using this equation, x moles. I don't know how many moles I need. And this is our volume, but I'm not going to put 300 milliliters. This is liters. So the unit down here has to be in liters. So 300 milliliters is 0.3 liters, 1/3 approximately of a liter. 0.300 liters. And then it's just algebra, so let's go ahead and solve that. So 0.3 multiply on both sides. Okay, so x is going to be equal to, and this is a bad light over here, so 0.3 times 2.15, and that's going to give me 0.645. So 0.645 moles of CH3CH2Cl. That's how many moles I need to make this solution, this 2.15 molar solution, with a volume of 300 milliliters. And so from here, I'm going to go ahead and do my standard stoich stuff and convert to grams. So 0.645 moles of CH3CH2Cl, convert to moles, by multiplying by the molar mass. 1 mole of this compound has a mass of, and so let's go ahead and figure that out. So 12.01 for the carbon. There are 2 of them, so times 2. And then there are a total of 5 hydrogens, so we can add 5. And then chlorine, plus chlorine is 35.45. Just kind of speeding this up now. 64.47. The molar mass of this compound is 64.47. Okay, so 0.645 times the molar mass, 64.47. And I get 41.6. We got 3 sig figs there. 41.6 grams of CH3CH2Cl. Okay? And that would be basically your standard way of figuring out, well, I want a concentration of this, and I want to make a volume of that. How much stuff do I need? Well, I got to figure out moles first, and then you got to go ahead and figure out the grams. And that's honestly, this is how I do every single solution in the class. When I do a lab with you guys, if it's got to be 0.5 molar, I may not say that, but I go ahead and figure it out, and I do it this way. I figure, oh, I need about 2 liters, and then it needs to be 0.5 molar, so how much do I need? And then I go through this whole process here. Okay. So that is their standard stuff with molarity. We're going to use molarity a lot over the next couple of days. What I want to show you really quickly, though, is what your homework is. It's due on Friday because that's what everyone's telling me to do. And I'm not really sure how that works, but there's an abundance of flexibility. That is what Mr. Durst is saying. If if something doesn't work out because life is happening, just let me know and everything will be okay. But the homework for today's lesson on using molarity and doing the calculations with the molarity equation, this guy right here, it is due on Friday. Let me go ahead and bring up the homework. So I got to use Firefox here, which is kind of weird. But if you go into the stoichiometry, into Schoology here and go into chemistry, you'll see chemistry online learning. That's a new folder, brand new. And then we've got some folders here for the next few weeks. These might go further down as we go further, I'm not sure. But for the first week here, March 17th through the 20th, I have 2 assignments already up here. This is the first one. So this is a 5-point quiz. I don't know how else to do it, but you go through here. I can see all your names, but the questions are right there. Okay, so there are 5 questions. And so like the first one says, how many grams of potassium carbonate are needed to make 200 milliliters of a 2.5 molar solution? Very similar to what we just did. I want to make it very clear here. Notice that it says only input the number, no unit. Okay, it's kind of unusual for me, I'm sure, but because there's so many different ways people can put the numbers in, I wanted to make clear you don't want to put in the unit. So it says grams. I assume that when you put the number in, you are putting in a gram unit. So input the number only. If that number is 21.3, then you put 21.3, not 21.3 G, as in gamma, just 21.3. And then you have 3 chances to answer the problem. If you have any questions, do let me know. I'm very happy to help you. Just send me a Schoology message or an email. I will probably check my email, and Schoology messages are there too, of course, at about like 8:30 a.m.-ish, and then probably once around lunchtime, maybe around 12 to 1 p.m.-ish, and then one more time after my daughter goes to bed, probably around 7:45 p.m. to 8 p.m. or even later at night. So at night I will check homework as well. Depends on what I'm doing that evening. Okay, and that's it for the first lesson. I'm going to go ahead and make the next one. So here we go. Have a great day.